All right, let's jump right into this explainer. Today, we're exploring the cosmic fingerprint. We're going to unravel the microscopic mystery of exactly how atoms produce the colorful light we see all around us, really breaking down the actual physical machinery ticking away inside the atom. To really figure this out, we have to start with a deceptively simple question. Why do atoms only glow in very specific colors? If you heat up the filament of an old-school light bulb, you get this continuous wash of white light, a perfectly smooth rainbow if you pass it through a prism. But if you pump a specific isolated gas, like pure hydrogen or neon, full of electrical energy, well, it gives you something completely different. It's a puzzle that literally baffled physicists for decades, and the answer fundamentally changed our entire understanding of reality. Because instead of that smooth rainbow, you get a literal barcode of light. It's fascinating. You have these perfectly separated, distinct lines of violet, blue, green, and red popping out against a pitch-black background. When scientists first started looking at energized gases through prisms, this is exactly what they saw. The red line is sharply defined, the blue line is sharply defined, and those empty, dark spaces in between them, they mean absolutely zero light of those intermediate colors is being produced. None. Every single element on the periodic table has its own unique, glowing barcode, just like a human fingerprint. But the burning question is, what on earth is happening inside the atom to make the light so sharply separated? Well, to solve the mystery of this glowing barcode, we have to rely on the core concept of things being quantized. As you probably already know, when something is quantized, it just means it's restricted to strict, discrete steps or values. Think about standing on a ladder. You can firmly place your foot on rung number 1, or you can step up and place your foot on rung number 2. But gravity absolutely will not let you hover in the empty air between them. You just can't do it. And in the quantum world, energy is that exact same ladder, built with rigid, unmoving steps. And we can actually see this ladder perfectly mapped out in the classic Bohr model of the hydrogen atom. You've got that central proton sitting right in the middle, surrounded by these orbital rings, labeled n equals 1, 2, 3, and 4. These rings are exactly like our ladder rungs. The electron is only allowed to travel on these specific paths. This was Niels Bohr's radical breakthrough back in 1913. He basically proposed that the inside of an atom isn't just some chaotic free-for-all. It has a highly strict underlying architectural structure. So, the absolutely crucial point here is that this map relies on two unbreakable rules. Number 1, electrons possess strict quantized energies. And number 2, they must remain at fixed distances from the nucleus, never ever existing in the gaps. Let that really sink in for a second. An electron can orbit on that first inner ring, or it can absorb energy to jump out to the second ring, but it cannot exist in the space at 1.5. It's physically impossible. The fundamental rules of the universe flat out forbid it from hanging out in the empty space between the orbits. It must instantaneously teleport, in a sense, from one fixed track to another. Now, zooming in even closer on those orbits, let's look at the exact moment light is actually born. Picture the electron sitting up high on a rung, let's call it E2. It's highly unstable up there, right? It really wants to fall back down to its comfortable ground state at E1. But here's the catch. Energy can't just vanish into thin air. When it drops from that high energy state down to a lower energy state, the leftover energy shoots out as a little squiggly wave. That wave is a photon, a literal physical piece of light. Okay, so this gives us the basic anatomy of a quantum leap in 3 really simple steps. Step 1, our electron gets excited, maybe by electricity or heat, and starts at a high, unstable energy level. Step 2, the electron plummets back down to a lower energy ring. Step 3, the exact, precise mathematical difference in energy between those 2 rings is dynamically spat out as a photon. Because the distance between the rungs of the ladder never changes, the amount of energy released never changes either. It's a strictly controlled transaction, and that exact transaction is the entire reason light from an atom even exists. And here is where it all perfectly clicks together, connecting the micro to the macro. Every single colored line on that barcode we were talking about earlier, it's simply a macroscopic record of an electron making a very specific microscopic leap. A massive energy plummet, say an electron falling from rung number 6 all the way down to rung number 2, releases a huge amount of energy, creating high-energy blue or violet light. But a smaller plummet, like just from rung 3 down to rung 2, creates the exact lower-energy red line we see in the spectrum. The specific colors we see are literally just a visible translation of the specific distances between the electron orbits inside the atom. It's completely deterministic. It's just a beautiful, mechanical clockwork happening invisibly right in front of our eyes. So this brings us to a mind-blowing realization. Since these specific light signatures act as literal, readable fingerprints that tell astronomers exactly what distant stars and planets are made of,
What other cosmic secrets are just waiting to be uncovered in the dark? Think about it. Because hydrogen atoms act the exact same way right here on Earth as they do in a galaxy 10 billion light years away. We can read the barcode of light from that galaxy and know with absolute certainty what elements are swirling around inside it. We are literally reading the chemical composition of the deep universe simply by understanding how one microscopic electron drops from a higher rung to a lower one. So the next time you see a neon sign, remember, you aren't just seeing a color. You are seeing billions and billions of tiny, perfectly synchronized quantum leaps.